Are you ready?
Okay.
Yeah, you need a second mic. There we go.
I don't think we need a second.
You don't need it? Okay. So, Theo and Shungo were selected among the Sprint CFP talks. So you submitted in March, and you were selected. So thank you very much. So it should be fresh information, recent developments. So you have the floor. Thank you.
Thank you. Hello, everyone. Today, we want to talking about our research called GPUGate repo squatting and the OpenCL anti-analysis to deliver HijackLoader. So first, quick introduction. My name is Shungo Kumasaka. I am a senior security engineer at GMO Cybersecurity by ELI from Japan. My main work is SIEM development. Next to me is Theo Webb. He is also a security engineer on our team. He is also focused on malware research. Theo will talk about the main GPUGate part later. So here is what we will cover today. First, the campaign overview and the timeline. Next, the delivery techniques. We called it repo squatting, and we will explain how it works. So after that, we will talk about today's main topics, the infection chain and the GPU-based anti-analysis. This is the GPUGate part. There are actually two versions. We will explain what the difference is. At the end, we will share how to detect this malware. Let me give you a quick overview of this campaign. The campaign was most active from September to October 2025, and then again in December 2025. The malvertising mainly targeted the EU, but we also saw infection in Japan. Who is the target? The fake installers for the developer tools like GitHub Desktop and the Docker Desktop. So on Windows, the malware uses a multi-stage loader that drops HijackLoader. Also, on Mac OS, victims get an armor stealer. In both cases, the attackers want to get a credential and the tokens. So developers are clearly the main target. Here is a timeline. The GitHub Desktop campaign ran from September to October 2025. Then in November, a new version of the GPUGate appeared. And from December 2025 and into January 2026, the campaign moved to the target, the Docker Hub and the Docker Desktop. So you can see the campaign keeps changing. One thing is those attacks use malvertising. For example, if you look at the sponsor section at the top of the Google search, there is a link for the GitHub Desktop. If you click it, you get a malware downloading page. However, if you look at the URL for this, it points the official GitHub Desktop repository for here. However, when we actually open that page, something was strange. I said that this page is GitHub Desktop official repository. But if you click the download link, you can see it is not an official GitHub domain. It is an attacker's domain. So if you download from there on Mac OS, you get a DMG file called GitHub Desktop macOS.dmg, which is an armor stealer. Also on Windows, you get a GitHub Desktop setup x64.exe, which is a custom loader for an info stealer. So how did the attacker get their link into the official repository? The point is GitHub's repository's network architecture. GitHub stores all repository, forks, and commits in the same repository network. This means a commit made inside a fork can also be accessed from the upstream repository. For example, if you fork the GitHub Desktop, that is an official repository, and they create a commit, the commit can also be reached at the GitHub Desktop tree, that is an official namespace. So, and once the commit exists, it never goes away. It means even if the attackers delete these forks, the commit is still there forever under the official GitHub Desktop repository. So we called these attacks is repo squatting. Here is how it works. The step 1, the attackers fork the official GitHub Desktop repository. Also, step 2, the attacker edit the README. They change the download link to point their own domain. For example, the GitHub Git desktop.app. And that the commit is now available to under the upstream repository. So the attackers deployed by a malvertising tool. Actually, GitHub does have a warning for this. When you visit the commit, you can see a message that says the warning for this. But the attacker can hide this warning. They just add an anchor tag to the URL, like a hash when can I get it, like that. And this makes the jump to start to the section of the README, and the warning is no longer too visible. So we reported this to GitHub, and they removed the malicious commit. On September 9, 2025, GitHub said their security team was aware of the issue and there was a work on it. But when we were preparing this slide, we tested it again. And as of April 6, 2026, the attack still works. So please be careful. This is still a real risk. Next, we wanted to check if the same things works on GitLab. If we fork a project and then try to open a forks commit from the upstream, we just get a 404 page not found. So that is a safe. Why it is? Because GitLab, when you fork a project, the namespace you choose is not part of the official repository network. It means it is separated. But there is still a way to get the commit into the upstream network. So if you make a merge request from the commit enters the official repository network. So on GitLab, the attacker steps up, forks, commit, then open a merge request. After that, the commit becomes visible from the upstream URL. So how do we protect ourselves? We recommend to check, make sure you are on the official default branch. Both GitHub and GitLab clearly show which branch is the default. Another option is to download installer only from the repository release page, not from the link inside the README. Okay, so that covers the campaign flow and the delivery technique and the repo squatting. From here, Theo will take over. He will explain the actual malware, the GPUGate campaign, in more detail. Thank you.
Hi, everyone. So I'm going to jump back basically to the malicious GitHub desktop installer that was delivered through the malicious commit. So in this next section, I'm going to focus on this part here that was marked as GPUGate. This involves one of the malware's more distinctive features, which is this GPU-based anti-analysis using the OpenCL API. And this was dubbed as GPUGate by Arctic Wolf, and hopefully you'll understand why shortly. So this malicious installer, just here, is a single file .NET application, which is basically just a .NET application with all of its dependencies bundled into a single executable. So this executes the .NET payload part from the overlay, and this isn't malicious, this is just how execution flows, which then makes several calls to this OpenCL API before decrypting an embedded payload. And these calls, they require the OpenCL runtime and a GPU. And this is really where the struggles began for me personally. So when I first started analyzing the malware in early September of last year, it wouldn't run in a VM or in a typical sandbox because there's no GPU obviously or OpenCL runtime. And I found what I thought was actually the correct decryption key, but I still can still decrypt it with that key. And what made it even more confusing is a public research report by some fairly well-known researchers came out, and they said it did decrypt it. So I was like, what's going on here? And I'm fairly new to security. At this time, it was probably my 6th month in, and before that, I'm self-taught. I had only been doing it for about 2 years, so my confidence was pretty low. And I was like, what's going on here? Am I understanding this right? And my only kind of conclusion I could draw was that this public research was actually probably incorrect, and there's something more going on here. So I mentioned about this GPU dependency, and this kind of pushed me to bare metal analysis. So we bought just a cheap second-hand machine with a GPU, and that kind of let me debug the malware and see what was going on. So in this next section, I'm going to explain what was happening here with OpenCL and how the attacker abused it. So to do this, I'm actually going to jump ahead here to version 2, which came out in around November, December. Version 2 specifically used this OpenCL API for decryption, but version 1 that was around in August, it used OpenCL for code misdirection, basically, to kind of obscure the real decryption key. So version 1's much easier to understand once you've seen a kind of typical OpenCL execution sequence. So I'm going to first introduce OpenCL through version 2. So what is OpenCL? Well, it's basically a C-based API that's used to write these small programs called kernels that are invoked by the CPU and then executed on a different device. And in this case, this is a GPU. In the malware's case, sorry, this is a GPU. So an OpenCL program, if you kind of visualize this, it consists of 2 parts. So the host program and then the kernel. And a kernel can just be thought of as just like a function that's compiled at runtime and then invoked by the host itself. And then a host obviously is just a traditional CPU, and the kernel then runs on an OpenCL device, as they're called, which is, in this case, in malware's case specifically, that we saw as a GPU. So this is an example of a kernel OpenCL kernel that I wrote. This is non-malicious. This is just for an example. And basically, these kernels are designed to run what's called work items in parallel on the GPU. And a work item is basically effectively one execution of this kernel, and it's the host who decides how many work items, how many of these kernels are executed at once. So, for example, you can see you've got this get global ID call in this kernel. And basically what this does is it retrieves this like a global index, and that determines, hey, which element should I process next? So, for example, you can see this example, it just it writes from a source to a destination, very, very simple. And this let's just say we call get global ID, it returns index 0. Well, that will write to destination 0. But in parallel, another kernel could be executing, and then that could also make this call. That would write to destination 1, and so forth. So what this means is basically the GPU can execute many of these work items in parallel on the device and do it incredibly quickly. So to talk a little bit about OpenCL memory, I'm only going to specifically go into global and private memory because it's specific to the malware that I want to talk about. But basically, global memory is basically allocated by the host and then used to store buffers which the GPU device reads from and writes to via the kernel. So to visualize this, it would be up here in the GPU device. Then you have private memory, and this is basically memory that's private just to the kernel. So if we jump back to the kernel that I was talking about, my example kernel, this I variable here, this would be in private memory over here. So it's just private to the kernel itself. However, you've got you see these global declarations in the function header. Well, this basically tells the compiler that source over here and destination will reside in global memory over here. So you have these different identifiers to specify it. Now, on Windows, OpenCL, the OpenCL DLL basically provides the various OpenCL functions used to write these programs or interact with it. And most systems have it installed, but hypervisors and typical kind of sandboxes don't, so they have a hard time running this sample. So OpenCL programs, really, whether they're malicious or not, tend to kind of follow a very similar kind of execution sequence. And in GPUGate version 2's case, it uses OpenCL to basically decrypt 2 embedded payloads. So I'm going to use version 2 as an example to explain this kind of typical execution sequence of an OpenCL program, and then how it can be abused for GPU memory operations. So if you see here on the right is the sequence of API calls used by GPUGate version 2 to decrypt the embedded payloads. So the first API call is to CL get platform IDs, and this basically retrieves the first available device vendor-specific OpenCL platform on the system. And this could be like NVIDIA or AMD's OpenCL driver that was installed alongside the vendor's graphic drivers originally by the user or what have you, or originally with the system. So next, CL get device ID is called with CL device type GPU. And this basically just retrieves the first available GPU device on the system. And then that GPU device is then used to create what's called a context. And to visualize this over here, this is done through CL create context, which it acts as like the environment in which the kernel executes and acts as like a link between the host and the GPU device itself so they can interact. So to actually execute that kernel and then perform operations on it later and stuff like that, a command queue is created with CL create command queue. And next, the malware, so the source code itself is provided as a text strings. So you can see here, this is the malware author's source code for the kernel provided as a text string. And then this is actually compiled at runtime into an executable kernel. So here's just like a tidied up version of that. Of the malware's kernel source code, but this is just basically a custom PRNG-based stream cipher to decrypt the payload center. So at this point, there's no reference to the kernel in the executable itself. So the API CL create kernel is used to create what's called a kernel object. And by doing this, you actually specify the name that the malware author used. So that in this case, this is stream decrypt. And you can see this matches the stream decrypt in the source code itself. So basically, this stream decrypt takes a pointer to encrypted data through this source, decrypts it, and then writes the result out to another buffer, which is destination. And that encrypted data, obviously, originally it belongs to CPU memory and isn't directly accessible to the GPU device. So what happens is CL create buffer API is used with CL mem copy host pointer to basically copy that encrypted payload into GPU memory. Likewise, down here, an output buffer is created with in GPU memory with CL memory write only, so the kernel can then just write back out to it for the decrypted payload. So next, the arguments are set up for the kernel itself so it can be called later. So for example, you can see you've got the source, which is pointer to the encrypted data, destination pointer to the decrypted data, the seed, and then encrypted data size. And these both match here in the kernel source to the API calls down here. Next, stream decrypt, the actual kernel itself, is invoked through CL-enqueue ND range kernel, which then actually starts the decryption process. And what it's important to note here, just in this call, you can see an argument work size is passed to it. And just before that, this is allocated the length of the payload. So this argument that's passed to CL-enqueue ND range kernel determines how many work items are run. So this is the same size as the length of the payload. So you can imagine you've got a ton of these kernels being executed in parallel on the device, and this means it can actually do the decryption incredibly quickly. So lastly, the decrypted data is then read back from GPU memory. Over here, it would be in global memory into CPU memory with CL-enqueue read buffer. So to put this all together, this is what the execution model looks like at a high level, but we've kind of been going through this, so I'll just skip this for now. So how does this affect dynamic analysis? Well, like I mentioned before, in like a typical sandbox or hypervisor, it just GPUGate version 2 can't run. You know, there's no GPU vendor drivers itself or the OpenCL runtime. But it can still be decrypted statically with a very simple Python script. As I showed, we could see the algorithm that they used. So, and in this case, they had hard-coded the seed as leet, and then you've got the data size itself. So, I mean, you can just put together a really quick script and decrypt it. However, anything after that, you can't execute the executable really. So anything after that, you have to statically analyze. So this kind of OpenCL acts as a blocker, and it can just act as a bit of a nuisance for any code after that, code to analyze after that. So now I'm going to return to the original malware, which is GPUGate version 1, to show how the attacker used code misdirection to obscure the real decryption key and mislead analysts. So here is the XOR decrypted kernel for GPUGate version 1. This is called generate key, and this basically takes what they've called it, the malware author called it a device name, and then checks basically down here whether its length is at least 10 characters. And if the length is less than 10 characters, a fake key is written to this output. Otherwise, a good key is written to the output. So after this output is then fed back to then decrypt the embedded payload. So it would appear that this good key is used to decrypt the main payload, right? So before this kernel is actually executed and invoked, like we saw in version 2, you have this kind of series of API calls that we just went through. And several calls are made to CL get platform ID and CL get device ID. So if we hadn't been just going through OpenCL for the past 10 minutes, you might assume, oh, okay, maybe these API calls are being used to grab a device name, and then that's being passed into the kernel for that length check. Well, neither of these keys can actually decrypt the payload. So, what's going on here? Well, this CL get platform ID and CL get device ID don't return device strings. They return IDs, So they're not returning like, I don't know, GeForce RTX 490 or something like that. Those kind of strings can be obtained, but through other API calls. Also, if like we looked at with version 2, if a device string were actually being passed into the kernel, as we had with version 2, you'd expect this CL create buffer being called with CL memcopy host pointer to copy that string into GPU memory. But here, if you look up here, this CL create buffer, this is being just called with a null pointer. So no host memory is being copied into that GPU buffer. So device name is just undefined memory, right? And then there's one final problem with this code that they've written. So you've got, I mentioned before, you've got CL set kernel arguments, which sets up the arguments to call the kernel itself. And basically, this expects its last parameter to be a pointer to the memory containing the argument's values for that call. I said a pointer, but here it's being passed by value. So this makes it look as though the kernel runs, but it never actually does. And if you look, all these API calls, they're not being error checked. So even if they fail, it doesn't matter. The kernel's not being executed. So as a result, the output buffer in that kernel is actually never written to, and then it just falls back to a 0 key. And it uses that 0 key to decrypt the payload. So GPU-based decryption is really quite effective against dynamic analysis, more so than static analysis, in my opinion. As version 2 showed, without this kind of code misdirection, obviously you can still decrypt it statically. Version 2, it wasn't too much of a challenge. But in version 1, the attacker used this kind of code misdirection to make that static analysis component a little bit harder as well. So in terms of like some static analysis tips, is really just questioning those unchecked API return calls for anything unusual. Obviously, trying a 0 key for decryption, that would have saved a lot of time, and reading the OpenCL manual. So next I want to look at really the differences between GPUGate version 1 and version 2 in terms of its early and then later execution flow. So GPUGate version 1, as I mentioned before, is this single file .NET application. And you can see it's 127 megabytes here. So despite this actually large size, it doesn't actually contain the official GitHub Desktop installer. This is mostly just binary padding to just imitate the size of the legitimate installer and make it a bit of a nuisance for sandboxes that limit the size on what you put into it. And then version 1 also uses more of like a staged delivery approach. So, for example, this first decrypted payload after that OpenCL code misdirection that we just went through is a very, very small payload just to retrieve this PowerShell script later. And then in version 2's case, they used a native C++ application with a huge embedded payload. The decrypted payload itself was 174 megabytes. So you can see it's like the executable itself was pretty much the same size. And this in itself contains this zip archive, which contains the official GitHub Desktop installer, which is executed, so the user's less aware really of what's going on, and HijackLoader. So it's more like self-contained. And you might laugh at this file, you might laugh at the file size being such a large size to decrypt, but like I mentioned before with OpenCL-based decryption, this is almost instant. When I ran it on my bare metal machine, you could barely even notice it was so quick. So continuing from this PowerShell script, in both cases, they use a kind of a similar PowerShell script. Basically, all this does really is just creates this marker file in temp to just prevent repeat setup, sets up some scheduled tasks to establish persistence, to just basically create a copy that runs at user login, add some Microsoft Defender exclusions, and then version 1 downloads this zip archive which contains HijackLoader and then extracts and executes it. I should say as well, in version 1's case, there was a ton of these PowerShell scripts that we found. And for example, like this, the temp marker file that they used, and then the scheduled tasks names, and obviously the attackers' domains varied largely. So I've put a list of these related samples and their differences together on slide 73, so please check it afterwards. So in version 2's case, really it's not too much of a huge difference, but unlike version 1, which adds these Microsoft Defender exclusions immediately, version 1 writes the exclusion commands to a separate PowerShell script that runs at user login. So really the difference is that version 2 doesn't apply the Microsoft Defender exclusions immediately, they're only applied afterwards. So not too much of a huge difference. But in version 2's case, it was self-contained. Obviously, they had this zip archive that was self-contained that contained HijackLoader, but it still had this PowerShell script that retrieved a zip archive. I wasn't able to obtain it, but I'm guessing maybe it was just like an updated version of HijackLoader or something like that, because it's so similar to version 1. So continuing from there into for version 1, like I said, it extracts and executes this zip archive containing HijackLoader, and this basically contains a series of legitimate binaries and malicious binaries. The first one being this control binary 32xe, which sideloads this legitimate but modified maliciously DLL, and this the directory it runs from up here, this sits under the Microsoft Defender exclusion path set by the PowerShell script. So as a result, these files can run without being scanned by Microsoft Defender. So in something like MDE, you might only see the process creation and then the DLL load activity. So from there, this Qt5 network DLL basically just reads an encrypted payload, decrypts it, and then module stomps this legitimate DLL, and then continues the HijackLoader's core functionality, which I won't get into because there's some fantastic research already out there about HijackLoader. But in both of these cases, they're just using a slightly updated version of HijackLoader each time. And as you can see down here with version 2, the flow is very similar. So like I said, it already contains the zip archive instead of downloading it, and runs the legitimate GitHub Desktop installer alongside it. So from there, they use the same malicious DLL, but modified slightly different, so it just loads and jumps to an RVA offset in this file association DLL that was maliciously modified here, but in version 1, this was actually the legitimate version. So when I was analyzing this, I just grabbed the legitimate version and then diffed it, against the malicious one to quickly find out the differences. So that was quite helpful that they did that. And then from there, it just follows the kind of same flow, general process as version 1, but then stomps a different legitimate DLL over here and continues the HijackLoader's core functionality. So these next two slides just give an overview of the infection chain in both cases, but yeah, please check those afterwards if you're interested. So next I want to look at some kind of a detection, like hunting opportunities for GPUGate version 1. So as I mentioned earlier, GPUGate version 1 is a single file .NET application. One of these, one way to kind of identify this type of executable is through a static variable in the file itself called the bundle marker. And this bundle marker, during the startup of this type of executable, the launcher checks this marker to see, hey, whether is this executable a single file bundle or not. And this marker basically consists of an 8-byte bundle header offset, which is shown here, followed by a fixed 32-byte bundle signature, which is the signature for .NET Core bundles. So if this header is basically non-zero, then the launcher itself will treat this executable as a single file bundle. So you can actually search for this bundle signature in GPUGate version 1 to confirm that this is actually a single file bundle. So immediately, so you can see here, this is the bundle signature itself. And then this matches exactly what was found in GPUGate version 1. And then just before this is the 8-byte bundle header offset, which is obviously non-zero, which confirms this is a single file application. So why is this important? Well, if you combine these two things, like the header offset and the signature, with other identifiers found in the malware, you can hunt for a lot of samples with Yara with this, and I found it as a really useful way, especially for version 1. I found a lot of them like this. So here's just an example of that rule. This was specifically the one that I used itself. So this rule basically checks whether this bundle header offset is non-zero and then confirms that bundle signature as a way to find it. So also, next I want to just check, go through some detection opportunities and kind of hunting opportunities for OpenCL kernels. So as I've showed, the attacker uses OpenCL widely across both of the versions that we've looked at. Now, OpenCL kernels, they contain actually a lot of boilerplate code. So for example, here you can see this kernel void, and you've got the get global ID function call that I mentioned, and just other very little pieces. So in both versions, you can see this. I've marked this here. And these can be, like I was mentioning earlier with the other YARL, this can be combined with other identifiers in the malware to hunt for related samples, or just other malicious kernels out there, because there is quite a few. So in version 1, I should say this kernel was XOR encrypted, but you can just still use like Yara's XOR modifier to get past this. So, for example, this is just an example of a rule that I wrote, and you've got the you can just use this kernel, this boilerplate kind of code, and just XOR modifier with Yara and stuff like that, and just get creative with this kind of rule, and you can find some interesting stuff out there. So next, I'm going to briefly introduce the new delivery technique that the attackers used during the December 25 to January 2026 campaign, and occasionally this is also popping up now and then, and through other various periods. But this specific campaign first appeared around December. So in mid-December of 25. some researchers at iSecurity SOC reported a very similar campaign that used, again, like we kind of saw before, these sponsored ads for Docker Desktop this time, to promote basically a Docker Hub installer page for Docker Desktop. So, I mean, again, we're looking at something incredibly similar. The download links, they lead to malware masquerading as the Docker Desktop installer, akin to the GitHub Desktop campaign that Kuma just described earlier. So I won't get too much into the malware because they're incredibly similar, but why do I think this is related? Well, we've got, again, OpenCL-based decryption. We've got binary padding to make it look like the legitimate installer. And again, the PowerShell scripts, they use this very similar format throughout the different versions that I showed you before. So it makes me think this is very likely it's the same attacker. I should also say, through other periods, through this campaign timeline, you see little bits of malvertising popping up, but you have these like heavier periods as well where they send the malvertising out on a more of a mass scale kind of thing, but they pop up occasionally now and again, even as of recently too. So in conclusion, we really recommend, just for users in general, to exercise caution around these sponsored search ads, and really for devs to download installers from the official release pages on GitHub, already vendor download pages. And for analysts, especially for dynamic analysis, for GPU-based malware, I highly recommend just buying like a cheap second-hand laptop with a GPU. For me personally, I found the easiest way was to just like set up the machine, set up all my tools and stuff like that, and then use like the free fog imaging software to create a disk image. So like if the machine gets screwed up or something, I make a mistake, I can just quickly revert back to it. Obviously, this isn't incredibly scalable, but I found this like a bit easier and safer than something like GPU pass-through or something like that. And as I mentioned before, in terms of static analysis, I really recommend to just question any unchecked API return values. Always double check for a 0 key. And if you come across something like version 2, you can usually decrypt it quite statically because it seems this attacker was hard coding their seeds. So thank you very much for listening. And on slides 66 to 73, I provided like a full set of all the identified IOCs because there's quite a few of them throughout this various campaigns. And if you're interested as well, please scan this QR code for our full analysis of GPUGate version 1 that was, I think, put out in January. Yeah. So yeah, here is all the IOCs. There's quite a fair amount of them. So yeah, thank you so much for listening.
Okay, questions?
Thank you for your presentation, very interesting. I was wondering if you wanted to try using VFIO with KVM to share either a physical GPU or a virtual GPU, and if you did it work?
I didn't try that, but like the reason why I went to this kind of just buying a cheap second-hand laptop is our company GMO Irai. We're like we provide a SOC as a service, right? So we had 2 of these incidents from our customers. So I was trying to respond as quickly as I could to try and get the IOCs and stuff like that. So I was like, okay, we need, I don't know what's going on here. Let's try and analyze this quickly. So that's why I kind of went that route. But I think I expect there's plenty of people in this room that know a better version, better way to do this more efficiently and more scalable way. So I hope that's all right. Yeah. Thank you.
Second question.
Thank you for your presentation. I never used OpenCL before, but do you think you could have patched the binary to make it run on a CPU?
No, I tried. It wouldn't work.
Thank you.
Okay, over there in center, Erwan, just 2 questions.
Thank you. You said that there was a publication about this that was erroneous. I was wondering what was actually wrong with it? Did you contact the author? And
so they like I said, they said the malware was doing a certain thing, and they were saying the decryption key did a certain thing, but it didn't, and there was quite a few mistakes in it. But I didn't want to like shame them, so I haven't really reached out to them or anything like that. I didn't want to create any animosity, so yeah.
okay, and it's not possible it was maybe the attacker publishing something?
No, they're a well-known security research firm.
Okay.
Yeah.
Last question.
Cool. I got the last question. You mentioned that in order to, or the GPU needs to be like an NVIDIA or AMD GPU or whatever. So I guess the virtualized VMware and those virtualized drivers won't work at all with OpenCL?
No. So like I can't remember what it's called, but if you do turn on the like, there's no setting that you can use in like any VM that I found that will allow it to run itself. Like you'll find the OpenCL DLL, but it will not execute. You need the specific GPU vendor drivers for it to run. I mean, I also tried to execute it in on a machine without like an embedded GPU, and it still wouldn't run. So the only time I could actually successfully have it run was with a specific second-hand laptop, a gaming laptop. So that was the only case I found it truly worked.
Okay, yeah. I also run a bare metal, but it has a built-in chip, so that's good to know.
Okay.
Thanks.
Thank you.
Thank you very much. Thank you.
Thank you.